Hold on one second. Okay. So there was one request. I think Manojit had emailed to look at some of the problems in the assignment. So I'm going to do two of them in this session, and then I can answer any questions you have or doubts after that. We'll go on for about 1 hour for this session. Okay, so we'll look at assignment 2. Let me just quickly show you. So there were these two questions. One, this one. Argya, can you confirm if you can see the screen?
Yeah, we can see that screen.
Okay, yeah. So this question was not about really using microwave office, but this was just about understanding the basic LC circuit resonators response and reflection. So this, of course, is a microwave office schematic. We've just connected a port to a parallel LC circuit, and the idea was to write down some simplified expressions for the reflection coefficient, and to extract some useful quantities like the resonant frequency, of course, is trivial, but looking at the shape of the response of the reflection coefficient in real and imaginary, and then identifying some special points. So basically, yeah. Hello?
Can you take the microphone a little bit closer? Actually, the volume is very low.
Oh, wait. Okay. Sometimes this happens because of the setting. Is it better now?
Yes, sir.
Yes, sir.
Okay.
Yes.
Yeah, sorry. I don't know. By default, the volume level on my Zoom goes to some low value. Yeah, so let me just repeat that again. So this problem was really more about writing down some simple expressions for the reflection coefficient for a very simple circuit, but a very commonly encountered circuit in microwave engineering. This is the parallel LC resonator measured in reflection. The schematic shown here is, of course, in microwave office, but this problem is about doing the calculations by hand. But I'll show you at the end that the expressions we calculate are actually matching, and also where they don't match. So the main point here is, this is just a bit of math, but the technique here about simplifying, that's why there are these hints given, because if you're not familiar with doing this kind of calculation, you might not necessarily be able to proceed with the rest of the calculation. So the hints are given, and I'll explain the sort of the motivation for why these approximations are suggested because of the conditions in which these measurements are typically done. Okay, so I'm going to shift to my iPad now. So I'll stop here. Okay. So just redrawing it for reference here. So the first thing, of course, is we want to write down the reflection coefficient measured from this port. This port has a characteristic impedance Z0, which I'm going to write as R, which is also 50 ohms. Of course, that really doesn't matter. The expressions are generic. And this is a very simple case of a port connected to a load, because there's only one sort of circuit element here. So I can basically consider this thing as Z of L, which is what I'm calling as my load. So for this very simple case, the expression for the reflection coefficient is also very simple. That's the basic thing you do. It's is ZL minus Z0 over ZL plus Z0, right? And already I've said Z0 is we're going to write at R, and ZL is the parallel combination of the Z of L and Z of the capacitance C. Now, just to write it down simply, we know that that the you know the resist when impedances add in series, it's easy to write, but when it's in parallel, you have to do something else. So one way of doing it is to basically say Z of L is 1 over Y of L, and Y of L is easy because admittance is inverse of the impedance. So you can just write down the admittance of each of these two elements. So the 1 over thing I'm going to write as inverse, and the impedance of L is j omega L. So the admittance is 1 over that. So it's that. So, and then the impedance of C is 1 over j omega C, and 1 over that is that. So anyway, it really doesn't matter. You can use the parallel formula, which is Z1 Z2 over Z1 plus Z2. It's also ultimately it'll just come out to be the same. Okay, so ZL is this expression. Now let's do some simplification. So I multiply it throughout by basically take the denominator as common. So, oh man, how is this doing it? Okay, so I then get 1 minus omega square LC over j omega L inverse, or j omega L over 1 minus omega square LC. Okay, so this is now Z of L. Now, most of the work now to get to some nice looking expression, which is easy to see, is just to use the simplification suggested in the problem. So the first thing is to write this in terms of two other parameters, which we have discussed many times in the class, which is basically in terms of the resonant frequency. So here already you can see that when omega square is equal to 1 over LC, this Z of L is going to be infinite, and that is basically the resonant conditions. That's the resonant frequency. So we already know that. So we use that omega naught square is 1 over LC. And we also use the definition of the characteristic impedance of a parallel LC resonator. So you have to remember these expressions are used for different things. But here I'm talking about Z of the resonator. I'm going to call that ZR, which is square root of L over C. Okay. This is the characteristic impedance of this parallel resonator. It has nothing to do with the port impedance of the thing. So that is Z naught separate. So this is just a reparameterization of the variables in terms of the resonant frequency and the characteristic impedance. And this is a natural thing to do because what you are interested in is the resonant frequency response or the response of this near the resonant frequency. So defining that basically gives you a natural way of, so it sort of becomes independent of the values of L's and C in some sense, except for this in the way it enters the Z of R. And you will see later on what role Z of R plays in the resonance, because you know that the only other parameter which sort of defines the characteristic of a resonance is the width of the resonance. So there is a resonant frequency which defines the position, and then there is the width of the resonance, and that is actually going to be related to the Z of R, but also to something else as well, which is, as we know, is the port impedance. Okay, so when you now write it like this, I can rewrite this as 1 minus omega square over omega naught square. Right, so just substituting 1 over omega naught square for LC over here. And just expand this. And after this, there was one more hint which was given. And in order to see how to use that hint, you write this denominator as like this. Okay. So far, we have only done substitutions. We have not made any approximations in the expression so far. Now, the approximation we are going to use is the one which was given in the problem, is that I'm going to write down omega naught plus omega as approximately equal to 2 omega naught. Now, why is this a valid approximation? Basically, it's saying that in the response of this resonator, we are only interested in values of omega which is close to omega naught, which is basically near the resonant frequency, because that's where all the action is. There is also a another implicit assumption which is not so obvious here, is that we are assuming the resonance is very sharp, in the sense that most of the thing happens in a range of frequencies which is very close to omega naught. And that is sort of typical for any resonator you are studying. Usually you don't have very broad resonances because those are not really useful or typical. So this fact that omega is always going to remain near omega naught, and there is a third sort of implicit assumption, and I'll just sort of comment on both the practical and there's a physics angle to it as well, is that we are assuming that value of omega naught is quite high, right? Because all of this stuff is relative. So if omega naught is very high and the range of frequencies omega is very small, then you know that the value of omega is always going to be near omega naught, and it's not going to be very big compared to that variation. So that's why writing this as 2 omega naught is okay. This we cannot change anything for the other term because that is the difference of the two frequencies, and that's actually now becomes the relevant variable because you're interested in variations of the response function near the resonant frequency. So this thing we cannot do anything here, right? So I'm going to now rewrite this as using this approximation, but this is essentially the same. This is equivalent to saying that omega naught or omega is equal to omega naught, right? But again, I cannot use this for the difference frequency, but I'm going to use it in the numerator. So I'm going to put that here also as omega naught. Okay, so this omega here has been changed into omega naught. I'm going to leave this here as the same thing, and I'm going to write this as 2 omega naught. Okay, so now this and this cancels, and I'm going to take divide both the numerator and denominator by omega naught again. So that gives me only 1 omega naught in the numerator, and in the denominator I'm going to have omega naught minus omega or omega naught. Okay, and there was this other hint given. I guess it was not a hint, but it was just an instruction to use a new variable, which is essentially this thing here, right? So essentially we are going to a different variable change, where instead of frequency we are going to go to differences of frequencies, which is with respect to the resonant frequency, and then divide it by the resonant frequency. Sort of becomes a dimensionless variable. So you know that at resonance this quantity goes to 0, right? That's basically the thing, and I'm going to call this as x instead of I think omega again, to just keep it separate. And if I use so this is now going to become x, but remember also that omega naught, so define this here as x, and also omega naught L is equal to sorry, 1 over LC into L, which is L over C, which is nothing but Z of R. So this is the other term in the numerator. I guess I've been using a capital R, or where did it go? Yeah, right. I think I tend to write it as smaller. I'll just delete this. So now you see that this expression has become extremely simple, that Z of L is J Z of R over 2x. Okay, so we have gone from an expression of Z of L which look like this out here to something much simpler. Okay, now remember that this is not an exact mapping. We have made this approximation here that the difference of omega naught and omega is very small compared to omega naught. So that only happens when the frequency is very high and the resonance is sharp. So this is sort of a typical scenario of any resonant. In some forms of physics calculation, you do something called a rotating wave approximation in these oscillator problems, and that is sort of equivalent to doing this approximation here. This actually changes in the complex domain, it changes the number of poles. So it actually creates a simpler thing, but this is not exact. But when will it work properly? When you are looking at the response of a resonator, which is very sharp, and you're looking at only frequencies close to the resonant frequency, which is anyway the region of interest. So it's okay, right? So after this, we will see in microwave office how these two things actually compare. So once you do that, now you can write down your gamma, and you can write down your Z naught minus ZL over, oh, sorry, the other way around. Keep forgetting this. So this, when you substitute Z naught equal to R and ZL equal to this new function, you write minus so gamma is equal to minus okay. So it's like 1 minus something over 1 plus something, overall minus sign. So now you see, if you look at this expression here, you see that X is a dimensionless number and ZR, which is the characteristic impedance of the resonator, divided by R, which is the port impedance, right? In this case, 50 ohms. So now you see that the role of the port impedance comes in connection with the characteristic impedance of this resonator. So this is the quantity which is related to the width of the resonance, which was one of the things you are supposed to find out later on. So here automatically you can look at some limiting cases. The resonance condition is of course X equal to 0. But when X equals to 0, both of these terms goes to infinity. So it's 1 minus infinity over 1 plus infinity. So that basically tends to 1. So gamma goes to plus 1, which we know from looking at these resonance curves that the real part of gamma, looks something like this, which goes from minus 1 to plus 1. And the imaginary part goes to 0 at the same resonance, which you can see here. So this basically tells you the response of gamma. And once you know this, it also asked you to calculate the points where the bandwidth, and I guess here there is a nomenclature confusion because that is also called gamma, but the width of the resonance is basically omega equal to omega naught plus minus delta omega over 2, where delta omega is the width of the thing, which sometimes is also called gamma. So, but that is basically this 1 over RC. This is the width of the resonance. So if you now calculate the value of omega at these 2 points, then you will see that these are the points where gamma goes to, sorry, I'm mixing words here. I mean gamma, if you calculate gamma at frequency omega, which is omega naught plus minus 1 over 2 RC, you will see that that's the point where it will go to 0. So these are these points here in the middle where gamma goes to 0, and that basically gives you the width of the resonance. That's what it was asking you to do, and do the same thing for the imaginary part of the wave function, or sorry, of the gamma reflection coefficient, and that goes to plus and minus 1. So this then, when you turn it into the phase, if you remember, I told you that the at resonance on reflection for a resonator like this, the phase goes from plus 90 to minus 90 degrees. So that's basically what the problem wanted you to work through. It then moves on to the case where you now add a resistor, another resistor here, which is called R internal, and then this is again connected to the Z0 50 ohms. So you just have to modify the expression, the ZL, by adding one more term R here, and you will see that R basically just gets clubbed into a new R prime here in parallel, and everything else remains the same for some part of the thing. But you see the sorry, let me say that again. You put that extra term over here and then redo this calculation, and you get a slightly different expression for gamma, which no longer goes from -1 to +1, but it will depend on what the value of this R internal is in relation to R. So that's what the problem was asking you to do. So let me stop this share now, and I will show you this calculation and comparison microwave office. Okay, so here's the simple LC circuit with the port connected, and I have used this global definitions for this problem just to show you. So I've defined a global variable for LR and CR so that I can use it in multiple locations. And then I've actually used output equations to basically plot that function, the one which I had written down, 1 minus j ZR over 2XR, using some tricks here. This is some advanced usage for the microwave office. I just show you, you don't have to remember this or anything. So there is actually an internal variable called this underscore FREQ, which is essentially the list of all the frequency points at which you're doing the simulation. So you can use it as an array, and then you can calculate like do manipulations on that. So what has happened here is LR and CR are defined globally. So I then calculate omega naught as square root of 1 over LC. There's a factor of this 10 to the minus 21 because L is defined as nanohenries and C is defined in picofarad. So that's a 10 minus 9 and a 10 minus 12. So that's where this comes from. Then this is just taking divide by 2 pi to just check the resonant frequency. It defines the Z of R. Again, there's a factor of 10 to the 3 because of the nanohenry and the picofarads value there. R is defined here. And then this is the list of frequencies for which the problem in microwave office. So this basically list is what you do from here when you go to project options and you define this list of frequencies. That's you can now access it as an array in this form. And now this X variable, which I had defined earlier for this problem, which was the difference of the frequency from omega naught. That's basically what's here. But here, the frequencies are in hertz, not in radians per second. But remember, it's a difference of frequencies divided by the same frequency unit. So I've turned everything into hertz. So it's frequency minus omega naught over 2 pi divided by the frequency. So this is now the dimensionless frequency, which is now listed out here. So now you have all the ingredients. And the just to remind you, the expression here was where do I do the annotation here? Oops. There, sorry. So to remind you, gamma was minus 1 minus j ZR over 2XR divided by 1 plus JZR over 2XR. Okay. So this quantity here I have defined here as IMG, that is here ZR without the complex J factor here, divided by 2x into R. And then I define the gamma, which is basically just 1 minus mg over 1 plus mg. But I have to define it as a complex number. So in microwave office, that function is basically this complex. In brackets, you write down the real and imaginary part. Okay. So the real part is 1, but 1 is not an array. So I just divided img by img here to create an array of ones. And then comma minus img because of this minus sign here. And then divided by the same thing, but without the minus sign because it's 1 plus this thing. And there's an overall minus sign here. So that now gives me gamma as a complex number, and complex numbers in microwave office are written as pairs of real and imaginary, which is what you're seeing here. So for each frequency here, this is the corresponding value of gamma n. Okay. So then all you have to do is create the graph. So the first plot here is the schematic to real part of S11, which is the standard measurement. So that's in blue. And the second one is the output equation, again, real part of the gamma, which we had just calculated here. Okay. So you see that these two match quite well. They're almost on top of each other. You can barely see the difference. That's the resonant frequency. When the value is 1, then these are the points which define the width of the resonance where they go to 0. And the matching is very good even beyond that, right? So this is because this is a sharp resonance. It's 5 gigahertz, and this from here to here is less than 100 megahertz. So that's what it means, that delta omega is small compared to omega. So the conditions we had set for this approximation are correct and valid. So if I now go and in the global definitions, change the value of L and C, and I'm going to do it in such a way that the resonant frequency remains the same. So I'm going to multiply and divide by the same factor. Basically, I'm going to do make this factor of 10, where that 2 came from. So I have, multiplied L by a factor of 10 and divided C by a factor of 10. So the resonant frequency is not going to change. So now you see, sorry, I'm having some bad allergies, so I'll be sneezing on and off. So now the resonance has become much broader, because remember, the capacitance has become small. And if you remember, the Q or the width, maybe since we just discussed the width delta omega is basically given by 1 over RC, right? So if C becomes smaller by a factor of 10, R is still the same, it's 50 ohms, then the width is going to become bigger by a factor of 10, which is what you're seeing. In fact, I need to adjust the sweep now over a larger range. So let's go from 4 to 6. Okay. So now you see the same familiar shape. It's much broader, but now you start seeing the deviation of this the exact function, which is the blue one, which is calculated as just the reflection coefficient, and the approximate function, which is the pink one. So you see it starts to deviate. So then, because now the resonance is much broader, see this here is going from 4.6 to 5.4. That's like about 800 megahertz on top of 5 gigahertz. So it's not such a sharp resonance anymore. So the approximation failure starts to show up. Okay. So that's basically what I wanted to say about this problem. Do you have any questions about this? Just give me 1 second to drink some water. So Manojit, you had asked for this problem. Is it clear now what
Yes,
it's
sir.
about?
Yes, sir.
Anybody else? Okay. So then I'll move on to the other problem in this problem set, which is again related to a resonator. Now, this one, the calculation I'm going to show you might seem very artificial because there are lots of approximations and things which are not so clear, but essentially, you will see that this is the way you can actually calculate an expression. So the main purpose of this problem is that we are going to consider a method to increase the sharpness of the resonance. Because remember that the delta omega, which is the width of the resonance, is only related to the R, which is this guy, and C, which is this guy, for the simple case where this did not exist, right? Which is the one we just looked at. So if you want to change the width, you don't have control over R because the 50 ohm is the standard. The only thing you can do is to change the C. And here it looks like the sharper you have to make it, the larger the C has to be. And then correspondingly, you have to change the L if you are keeping the frequency constant. Now, this might not always be practical. The value of L's and C's you could choose in a particular example might be fixed because of whatever maybe the values which are available. So does that mean that if L and C are fixed and R is fixed because of the 50 ohm environment, then you cannot do anything else to make the resonance sharper? Answer is no. This is how you do it. You introduce this coupling capacitor, which essentially decouples this resonator from the 50 ohm port. So remember again that the 50 ohm port is basically the same as having a resistor to ground with value 50 ohms, right? So the one way,
Sir.
yeah.
So this is the point where I have the doubt that how can you say, I mean, we have the 50 ohm resistance, after that we have the source, and
no,
this 50 ohm
we don't have the source after that. I'm just sort of drawing this in shortcut here. The correct way of drawing this is like this.
Yes.
Okay, because this here is basically what this port represents, and this is 50 ohms. But if I forget about the voltage source, and remember this is the idealized model, right? This is what is called as the Thevenin equivalent. So in that case, the voltage source has zero impedance. So if the voltage is set to 0 and has 0 impedance, then I can just remove this voltage source. Then all I have left is the parallel LC circuit connected to 50 ohm to ground. Okay. Is that part clear now?
Yes.
Now, the way to, I mean, there are many ways of looking at it, but one simple way of understanding this, that this R is introducing the dissipation in this oscillator. So whatever energy is contained in the oscillator has to dissipate via this R. So if this was directly connected to the 50 ohm, the dissipation is sort of maximal. It will extract energy a lot faster. But if I put a very small capacitor here, then that actually reduces that rate of dissipation. Because if they make the capacitor smaller and smaller and the limit of capacitance going to 0, this impedance Z of C will go to infinity, because it goes as 1 over omega C. And that basically is saying that this LC oscillator is not connected to anything. It's isolated. So that's the case of no dissipation. And if the C is very, very large, or if you replace this by a short circuit, then you have maximum dissipation. So by choosing the value of this coupling capacitor C sub C, you can control the amount of dissipation experienced by this resonator. And that is basically the same as saying that I'm increasing the sharpness of the resonance, because the smaller the dissipation,
the sharper the resonance is going to be. So the purpose of this calculation is how to compute the new sharpness, because the old sharpness, we know if it was directly connected, that delta omega is 1 over RC. Now I want to compute what is the new delta omega prime, given that I now have introduced this capacitor C here. Okay, so I think we had also discussed this in class. This is I discussed, draw the series combination of the coupling capacitor. So what is that talking about? It's basically talking about the circuit seen from this point of view. So from this point of view, you have a capacitor and then you have a resistor to ground. Okay, this is what the circuit, the LC oscillator is seeing. For, this is the dissipative part of the circuit. So it says that redraw the series combination of the coupling capacitor in the 50 ohm 40 ohm as a parallel combination with the capacitance value CC and the resistor R. Okay, I should maybe really call that R prime because I'm using R for the original resistance. So it's saying treat this as, so this is C of C, this is R, which is 50 ohms. It's saying rewrite this as this circuit. R prime, and this is already given that this thing is the same as C of C. So this I'm already giving you. I mean, one can argue why this is the case, but you'll see that this gives you the correct answer. So if I make this model, and what is the reason for making this model? Because in this model, the new circuit combining everything becomes this. It's L, C, C prime, sorry, CC, and R prime. I know how to calculate the delta omega of this guy, because this circuit is just a simple LCR circuit. All I have to do is I have to replace C by C plus CC, because these two C's are in parallel. L is the same, and I have R prime in parallel. I know how to write down the expression for the delta omega. So delta omega prime is 1 over R prime C plus C prime, sorry, C plus CC, right? That's it. But what is the quantity I don't know here yet? R prime. So I have to calculate R prime using this idea that these two circuits have to behave identically. Remember, it's not that I'm just randomly drawing this. I would like to calculate the value of R prime such that the impedance or the admittance of this circuit is the same. Okay, that's basically the thing. And you had to make some or realize that some assumptions which have to be made here just based on the requirement of the problem. So that's basically the things you had to think about, that how can you even do this? This is, see, the reason it looks very silly because the two circuits are completely different, right? One is a series RC circuit, one is a parallel RC circuit. So how can they have the same frequency response? So this is where the first thing to realize is that we are studying a resonator. So just like in the last problem, it means that you are interested in the values of these things only near resonance. So that's the first approximation you think of, that, okay, I don't clearly, if I write down the expression for Z, which is the impedance or the admittance of these two circuits as a function, and this is going to be as a function of omega, they are not going to match everywhere. And there's no way you can choose any of these parameters that they will match everywhere. And they cannot, right? This is really an approximation for writing this parallel series LC circuit as a parallel circuit at one frequency. Strictly speaking, we are just really going to say that I want to just match it at the resonant frequencies, because I'm going to assume that, okay, this is going to be a slow function it's not going to vary so much around omega naught. And since I'm only interested in the response near omega naught, that's a good enough approximation. Okay. So forgetting which one I'm writing on, which one I'm not. Let me clear the screen. Stop share here. So we write this again. So C R, this is CC, and this is R prime. So one thing you should already realize that the moment you put a coupling capacitor of this type, so maybe just for reference, let me write that down here. LC CC. The moment you put the CC here, because in the equivalent model, this CC comes in parallel to the original capacitance, it's going to change the resonant frequency of this resonator. But there is this assumption that C of C, it's not assumption, that's sort of the conditions. C of C should be much less than C. And that bodes well because whatever C is, if C of C is much smaller, it's a small capacitance. And that is, we want a small capacitance in order for the resonance to become sharper. So that's typically the limit under which you work. And that also means that the smaller the CC is, then C plus CC, which is the new capacitance, is going to be close to CC. It's not going to be too much different. So it's going to be close to C. So the resonant frequency is going to shift by a small amount, which is related to how small C of C is. That I think it'll get very confusing if I say CC and C of C. Let me just rewrite these as C primes so that this is not going to be confusing while hearing. So this is C prime, this is C prime, C prime. Oops. Okay. So now it's just, again, some simple manipulations and making the approximation. I'm going to again use the admittance approach. So I'm going to write Y of P, and this is, I'm going to call this whole thing with subscript S, and this is with P, basically stands for series and parallel. Okay, so Y of P is basically this parallel combination. So it's the sum of the Y's. So it's 1 over R prime plus J omega C prime. And Y of S is 1 over Z of S, which is 1 over R plus 1 over J omega C. That's just a series combination of R and C prime, which is J omega C over 1 plus J omega CR. Okay. So the first approximation is I'm going to set everything to omega naught. So that I'm not going to worry about the frequency variation. I'm going to calculate and make this equality only for this frequency. Okay. And the other one, which anyway we have done, that C prime is the same, that is already done. So now we get Y of P is 1 plus J omega naught C R prime over R prime. Okay. That's just this, taking this expression and taking a common one. And Y of S is J omega naught C prime over 1 plus I can now write as omega naught square c square r plus c prime square naught c. So now I do the equivalency that this is the same as this. And you do this, use the fact that C prime is very, very small, which means that 1 over omega naught C prime is going to be much, much greater than R. So remember, omega naught C prime is essentially the impedance of the series capacitor, right? And because C is small, that impedance is going to be much greater than 50 ohms. That's sort of the condition under which we are working. This essentially implies that omega naught C R is much less than 1. So essentially, we can now throw away some of these terms here in the denominator. So I get now, I'm going to be equating these two things. So I have omega naught square C square R over 1 plus, sorry, C prime omega naught square C square C prime square R square. So this is the part which we had said is very small. So I'm going to set that to 0. Then I have J omega naught C over C prime 1 plus again 0. This is the other term, which is equal to 1 over R prime plus J omega naught C prime. So these two also cancel. And then you're just left with the fact that R prime is 1 over omega naught square C prime square R. So you now have a nice expression for this new effective parallel resistor R prime, which is 1 over R. So that's kind of somewhat unexpected, that it's inversely proportional to the original R, which was actually causing the dissipation, right? So it's like the original R was smaller, this would be even bigger. So it's kind of unexpected. And then it goes as 1 over omega naught C prime square. So remember, omega naught C prime is the impedance, imaginary impedance of the series capacitor. Here, of course, there's no J or anything because the imaginary part cancelled out on either side. But now you see that if C prime is much less than 1, which implies that 1 over omega naught square or omega naught C prime square is going to be much, much greater than 1, which means that R prime is going to be much greater than R. And this is exactly what we want, because delta omega is going to be 1 over R prime C plus C prime. So if R prime is much larger than R, that means that delta omega prime is going to be much smaller than delta omega, which is the value of the width without the coupling capacitor. And you actually see that it goes as the square. So if you double the capacitance, the Q will become the width will become double. So that's basically the calculation you're supposed to do and show this by using this fact that it is there. So now you know, because this is very useful, because now you can target how much value of C prime you need to do to get a particular value of delta omega. So as long as you're in this regime that C prime is very small, then this formula works out quite well. So here again, I did a little calculation in Microwave Office to just verify this. So here's the so the top part is the circuit. You have your L C coupling capacitor, which is defined as 0.05. And then I've also defined another circuit with the same C of C and this resistor to ground, 50 ohm resistor to ground, which is now the series RC circuit, which I'm interested in looking at, right? Just to do the comparison. Then where is the oh sorry, so I just again defined these quantities, omega naught as 2 pi f. So here I've actually used the exact resonant frequency is not 5, it's very close to 5, so I've just used this, but I could have just defined this as 1 over square root of LC as well. Capacitance here, CC1 is this, just to turn it from picofarads into farads, R is 50, Rp, which is the R prime, is 1 over omega naught square CC1 square into R, and that gives you this value 8106. If I take the inverse of that, it gives me this, like inverse of the real part of the admittance. So in the schematic, all I did was plotted the real part of Y of in. What is Y of in? Is basically the effective admittance real part of that. The inverse of that is basically the same value as the parallel, because here I'm just calculating the real part of this circuit at that particular frequency, and I've just plotted it as a function of frequency over here. And remember that we only chose the value at one particular point, so you can see that it does vary from frequency to frequency, but we used this value. So this was just to show that the value this thing calculates, something like 0.00012226, is matching with the number we calculate from the formula we just derived, which is basically 1 over Rp. And the smaller the capacitor is, the larger this value will be, and the sharper the resonance will actually be, which is, I think, also plotted here. So this is the sharp resonance you have. If you remember that it's now actually going from +1 to -1, as opposed to, let me just zoom in here. Okay. So this looks almost exactly identical to, okay, I guess I've changed the frequency here. It doesn't. Let me. What's this? So I'm just showing you the standard LC resonance again, just for comparison. So remember, this one goes from -1 to +1, whereas this guy is going from +1 to -1. The reason for this is the extra coupling capacitor, which acts like also an impedance inverter, like the negative sign comes in because of that. But that really doesn't have any meaning overall. It's an overall negative sign. So that's why this is there. And now this resonance is much sharper. The frequency will shift if I change the coupling capacitor. So if I now go back to this guy here and okay, the tuner is already there on that. The coupling capacitor is it's this one here. So if I increase this, the frequency becomes lower. And you can see that this width here, this width from this point to this point, which is basically the width of the resonance, increases as I increase the capacitor. So it's sort of becoming broader and broader. So you can already see it at this level, because it goes as the square of that function. And as it becomes smaller, it becomes sharper and sharper, and the frequency moves higher. Because now the total new frequency is the sum of the two capacitances. Okay. So yeah, so that's basically the for this particular problem. So I'll stop there for tonight. Are there any questions or doubts here about this particular thing? And this formula is very practical because this is how you estimate how much coupling capacitor you need if you want to get a certain sharpness in your resonance. Of course, one can use a software like Microwave Office to do it for you, but if you had to calculate it, this is how you would do it. And those approximations are again related to the fact that it's a resonator. You're interested in response near the resonant frequency, and everything is sharp. So you don't worry so much about the fact that you're using a fixed frequency, even though it's not really correct. Okay, so is this clear? Okay, all right, yeah.
When we add and change from a series resistance and capacitance to a parallel resistance and capacitance, so there we have to do this apply the Thevenin's theorem. So at some point the
No. Sorry, there is no Thevenin's theorem being applied here. Here, it is just a model.
Okay.
Okay, I'm just saying I want to treat this as a parallel RC because I know how to compute the line width, the width of the resonance for the parallel case. For this kind of a series capacitor plus the resistance, I don't really know. It is the reason it's that the model works is that you're only forcing it to be equal at one frequency.
Yeah.
Otherwise, this is just completely garbage. It has no meaning to make these two equivalent. It's not like a Thevenin equivalent or anything like that. I'm just saying I know this circuit, how to calculate for this circuit. So I'm going to just make the two equal. But because I'm doing it at only one particular frequency, it's really just in some sense, it's a math trick, which in the circuit form looks kind of strange. And because you're doing it at only one frequency, it doesn't matter. So, this resistor R prime, it's not a real physical resistor. It's essentially it's saying how much dissipation you're going to get because of this extra series capacitor you put in front of the 50 ohm, which is basically what the Microwave Office simulation was calculating. See, there I was doing the full calculation, which is this. Let me show that again, which is basically this Y in of 2 is basically that calculation, right? Because it's saying I'm looking at this circuit, which is a series C and a series R, and I'm going to look at how much is the input admittance and the real part of that. Why the real part? Because that is the part which is going to give me the dissipation. So I just added this R and C in parallel, and I equated it just to compute this value of R. And we see that it matches very closely to the full exact calculation. And again, it works because it's one frequency and you use the approximation that C of C is very, very small. Otherwise, this calculation would give you some errors if C of C was not very small. So it's not a transformation from one type of circuit to another circuit. We're just assuming an approximate model and forcing it to be equal in this case. Okay. All right. So I'll stop this and I'll upload this tonight in the same location. And the next revision session is again tomorrow night, right? Same time. So I will pick a few other things and do that. And tomorrow I will again be in my office from 11 to 1 if you want to come. I don't know. I just sort of chose that time. I realized some of you might have classes, but just drop me an email. I'm going to be leaving campus around 3 o'clock. So it has to be before that. Otherwise, we can also discuss later at night after the revision session and also sometime on Friday if you have any specific questions you want to ask me. Okay, I will stop.